Some examples for Module 2, we're looking at things like voltage dividers and current dividers and parallel series combinations, and then finally node voltages. All right, so some good circuit solving techniques here. So let's look at this circuit. Let's say we want to find V1, V2, and IS. And we're going to have 3 or 4 different ways of going about this problem. So we're solving this circuit. So we're going to do it several different ways. Normally you probably wouldn't do it several different ways, pick your favorite way kind of thing. But just for practice, I think we'll do that. Okay, so this circuit has one source and a bunch of resistors. So in general, when you have a circuit where you know the sources and you know the resistances, you can solve the circuit somehow. All right, there might be a lot of equations, might take a lot of work, but you should be able to do it. Even if it's a very large circuit with a bunch of sources and a bunch of resistances and so forth. Okay, so let's first off just kind of take the brute force approach, I don't know, of doing parallel series combinations and then a bunch of equivalent circuits and Ohm's law to try to figure out what these things are. And so this circuit, if we want to, so we know stuff about the source, and so we kind of want to start finding things around here first and then working our way out. I guess maybe the first approach I would say is let's go ahead and start with finding the equivalent of all of these resistors, and then we can just have a circuit, very basic then circuit, where we have our 12-volt source still here, and we still have our source current because the IS is a current in the source, and then we'll just have some big R equivalent, or let's just call it R total, and it's going to be all of those resistances put together. Okay, so this is good practice for parallel series combinations like we learned in physics. And so what do we have here? So looking at this circuit, hopefully you can see these two, 3 and 4, the 3 ohm and the 4 ohm are in series, right? Current's flowing through here, through the 3 ohm. It has nowhere to go, can't escape anywhere, it has to go through the 4 ohm. So they are in series, right? So we can combine them in series. Once we combine those in series, we can think of one resistor in series. Now that combination is in parallel with the 8 ohm resistor. Okay, do you see that? And so once we combine those, then that combination is in series with both the 2 ohm and the 5 ohm. So let's go ahead and I guess let's draw this in stages. At least for this one time anyway. All right, so the first thing would be put the 3 and 4 in parallel with each other. In series. All right, so we still have the 8 ohm here, we still have the 2 ohm here, we still have the 5 ohm. Vs, or 12 volts, I guess. But now these two have been squished down into 1, right? And so if we call this R equivalent 1, R equivalent 1 has to be what? It's just to be the same. We want the circuits to be the same. So these other elements out here, this side of the circuit doesn't know that there's any difference between the 3 and the 4 in series and R equivalent, right? And that's the whole point of having equivalent resistances. They act the same electrically to the rest of the circuit. The rest of the circuit doesn't know. All right, so for that to happen, we know that resistors in series add, right? So it's going to just be 3 ohms plus 4 ohms. All right, so R equivalent 1 has to be just 7 ohms. All right, and the rest of the circuit will not know the difference. Now, like I said, once those two are combined in series, now these two are in parallel, right? Both the lower ends are touching and the upper ends of both of them are touching each other, right? So these two, the 7 and the 8 ohm resistors are in parallel with each other, so we can mush them into one resistor. All right, and then the rest of the circuit doesn't know the difference. IS is still here, 2 ohms is still here, 5 ohms is still here, but now we got maybe R equivalent 2, right, is these two mushed together, where this one is those two mushed together, but still we're simplifying, right? And so R equivalent 2 is 7 in parallel with 8, right? Remember how to do parallel combinations, if there are only 2, multiply on the top, add on the bottom. All right, so we got 7 Come on, calculator. 7 times 8 divided by 7 plus 8. What is that thing there? Okay. So R equivalent 2 is 3.733 ohms. Okay. Now that we've got this melted down, conglomerated down, these became one. Now hopefully you can see that these are all in series. The 2 ohm, if there's any current, IS is the current. In the 2 ohm, it has nowhere to escape. It can't go anywhere, no Y's, no places for it to go. It all has to go through R equivalent 2, and then all that has to go through the 5 ohm back to the source. So there's only one loop here, and so these are all in series with each other. Okay, so we can then get our total. Has to be just a series combination of those two. 2 ohms plus R equivalent, 3.733, plus the 5 ohm. Right, so our total just becomes 10.733 ohms. Keeping too many sig figs here, but for a bit we'll be okay. All right, so our total here is, we can just say 10.73 for now. 10.73 ohms. Okay, and so now we've got a nice little simple circuit, and we've got the voltage top to bottom. Remember, this long bar means the plus, and so we've got the voltage across resistor and the current through it, and so we can just use Ohm's law. It says that the 12 volts equals IS times R total. Doing Ohm's law for this resistor here, and so IS we can solve to be 12 volts over 10.73 ohms. Okay, so 1.1, let's keep 4 sig figs until we go to an answer. So 1.118 amps for IS. Okay, so if looking for the answer, we say 1.12 amps. But to help with rounding errors, we'll keep 4. Okay, so we got IS. It's the same IS in all of these different circuits. So we can go back to this circuit if we happen to be asked for what's the current in the 2 ohm resistor. We've got it. It's IS. We can calculate its voltage. V equals IR if we wanted the voltage there. We're not asked for the voltage there. We're asked for V1. What can we do to get V1? Well, let's go ahead and name these voltages here. And I'm naming them with the current. So if you think of the current flowing around like this, I'm naming them so that resistors have positive sign convention when the current goes into their plus, right? And so we can write Ohm's law nicely for them. Okay, so let's go around the loop here. And so let's just start here. Let's do KVL. KVL of the right loop. Okay, so when you're doing homework, write out what laws, what rules, how you're getting the equations, and be sure to write out your equations. So let's start here and go around. Remember, when we do KVL again, we walk around, and when we hit a negative sign, we put a negative sign in the equation. Hit a positive sign, we do a plus in the equation. Okay, so starting there, we're going to get negative 12 volts, and then we're going to get plus. And so what are we going to put here? We could give this a name, call it VA, VB, VC, VD. We could do that, or we can just kind of, as we're going, do Ohm's law here. So this is going to be, what does Ohm's law say? V equals what? V equals I times R. So this is going to be IS times 2 for the voltage, and this one's voltage is going to be IS times 5, or 5IS, 2IS. And so we can just, as we're going around here summing voltages, we can say 2IS. Then we're going to hit here plus V1. We don't know the current in here because IS comes here and it splits, right? And so we don't know the current here, so we can't do an IR for this one, but we have it named V1 is one of the things we're looking for. So plus V1, and then we're coming into the plus side of this one, 5IS. And as we come back, we get to where we started, equals 0. We climbed up a mountain, came back down the mountain to the same place we start. Our altitude is the same thing as what we started at, right? equals 0. Okay, and so we have an equation now with IS and V1. Oh, and we know IS. Okay, so we can get V1. So we got V1 then is 12 plus 7, 12 minus 7 IS. V1 on this side, take everything else to the other side, yes. 12 minus 7 times 1.118. .17. Oh, let's keep the 4 too. 4.174 volts for now. For the answer, version 1, 4.17 volts. But we might need this one to calculate V2. Okay, so we got IS, we got V1, we still need V2. So can we, just as another point, we could have, if we wanted to, figure out a way to calculate V1 from this circuit. Where's V1 in this circuit? It's also right here. V1 is still right here, right? It's always a voltage across this combination, right? This is the voltage here. It's also the voltage across those two, right? So we could have used this circuit to calculate V1 if we wanted to. We would get the same results. Okay. V2. How do we want to get V2? So V2 is over here. It's not in any of these circuits because we lost it in the first series combination that we made here. So we should use this big circuit somehow. How do we want to do this? We know V1. So if we knew the current, we might have to go ahead and name a current here. Let's go ahead and name a current. Let's just call this IA. And so if we knew IA, we could say V2 is just IA times 4, IR, right? V equals IR. But we don't know that current. We don't know the current here. We know IS. So we probably should find the current here. I'm going to have to do another name. Let's call that I1, I guess, because it's going through the same thing that has V1. All right, so if we knew I1, we could figure out IA, and then we could get V2. That's a plan. There are many ways to do these equations, but let's do KCL at top center node right here. If we do KCL right there, what does it say? KCL says in equals out. What's coming into this node? Just IS. What's going out? I1 and IA. All right, so we know IS, but we don't know I1 or IA, but we can get I1. I1's easy at this point, right? Why? Because we know V1 and we know R. So ohm says V1 equals I1 times 8 ohms, right? V equals IR. So I1 is V1 over 8. And V1 is the 4.174 over 8. So I1 equals 0.5218 amps. All right, so IA is IS minus I1 is 1.118 minus 0.5218. 2 may say figs, but anyway. So IA is 0.596 amps. Okay? Not anything we were asked for, but now we can get V2, right? So what's V2? Ohm says V2 equals IA times 4 ohms, right? So V2 is 0.596 times 4. So that answer times 4. So V2 equals 2.38 volts. All right, so we got our 3 variables we were asked for. So this is just kind of the ad hoc brute force, do what you can do method for finding it, for solving a circuit. Let's try a little bit different method. Let's try a voltage divider method. All right, so let's go back to our circuit here. Let's try a voltage divider method. All right, which is still a little ad hoc, but it'll be maybe a little more uniform. I don't know. So when we do a voltage divider, we have to know a voltage, and then we have to have combinations of resistors in series, and we know how things break up. Is the video still working? Okay, my computer's acting weird. So that's what we have here. We have a voltage source, and then we can use this. If we look at this circuit, maybe, hope that's easier, we can see that we have a voltage source and we have 3 resistors in series, and so we can get how the voltage divides up among these resistors. Okay, one of them being an equivalent resistor. And then if we look at this circuit, if we know V1, we know the voltage across from here to here. So that's the voltage across these 2 resistors, and so we know the voltage across both of them, so we can use a voltage divider. Since they're just series resistors, no other things in there, then we can use that to get the voltage on get V2, right? The voltage of any one of those 2. Okay, so let's start by redrawing our circuit for the voltage divider idea. And so let's redraw it with the source out here. Right, because it's the big voltage. We kind of like to have voltages up and down. You think of them as levels. And then we've got these 2 resistors. Let's just draw them like that. Okay, one is connected to the top of this 12-volt source, right, where IS goes through first, and really doesn't matter when they're in series which one it goes through first or last. But so this would be like our 2 ohm resistor, and then this would be like our 5 ohm resistor. And then we have this parallel combination of stuff. One part of the parallel combination has one thing in it, and the other one has these 2 in it. Alright, so I'm just redrawing the circuit, not changing anything. Hopefully. Trying not to change anything. And we have V1 is positive up here, kind of the same way that the 12 volts is positive, so that's V1. And V2 is the voltage across the 4 ohm. Like that. V2, come on. Okay. And so this is the same circuit, just redrew it to kind of see things in series and parallel, maybe a little bit easier. Feel free when you're doing these problems, redraw your circuits. Redraw them correctly. Make sure everything all that matters is what's connected to what, right? How they're connected. Doesn't matter if you have a long looking wire or a short looking wire, or if there's square corners or round corners, right? It's the connections that matter. Okay, so for this voltage divider, if we can kind of see now that we have across this voltage source, across this 12 volts, we have this element, we have this, if we think of it as one conglomerated element, and then we have this element. And we already did we find that? We called this R equivalent 1. No, we called it R equivalent 2. Yep, so when we made this into one R equivalent, we called it R equivalent 2. So I'm going to cheat a little bit, but it is basically 8 ohms in parallel with 3 plus 4 ohms, right? These 2 combine in series, so they just add, they become 7 ohms, and then so it's 7 in parallel with 8, right? And so that is how we got the 3.733 ohms. Okay, so that is, if we want to, I guess we'll just redraw the circuit. If we want to apply our normal voltage divider equation. Now we've got 2 ohms, we've got V1 is across here, and this is the 3.733 ohms, and this one is the 5 ohms. And the source is still 12 volts. All right, so we can use our voltage divider because we got a voltage, a known voltage across resistors in series. So that's the requirement, and we can do that for the circuit. And so voltage divider equation says the voltage we're looking for, which is V1, is going to be the total voltage. We can just say V source for a general, times the resistance of where the voltage is we're looking for. So we call it R equivalent 2. And then what goes on the bottom is the total. So it's a ratio, right? Voltages get shared, bigger resistors get a bigger share, right, of the resistance. So it's just a ratio. So we have 2 plus, it's called R equivalent 2, I guess. 2 plus R equivalent 2 plus 5, right, is the bottom, is the total resistance. And we could have 100 things in series, or however many things are in series, we add them all up on the bottom. If some of them have combinations, we might have different parallel combinations that went into making this, we could have, and this, anyway. So, but if we can get them all conglomerated down into a set of things in series, that's what we put down here is the total resistance. Okay, so we'll do this. So V1 equals 12 volts. Our equivalent one was the 3.733 divided by 2 plus 3.733 plus 5. So we can get V1 12 times 3.733 divided by, in parentheses, 2 plus 3.733 plus 5. Okay, so we get 4.17 volts. Which, hallelujah, that's what we got for V1 before, so that's good. Okay, now what about V2? Well, now looking at this circuit, we know V1 is the voltage across these 2 resistors, right? And V2 is the voltage of just one of those, so we can do a V divider again. And remember, voltage divider just comes from Ohm's law and KVL kind of stuff. It's no magic. It's just a shortcut because somebody did this math so many times, decided to make an equation out of it. All right, so in this case, V2 is going to be the total voltage across those 2 resistors, which is just V1. And then the resistance of where we're looking for the voltage, so it goes on top, so that's 4 over the total, 3 plus 4. All right, so V2 is 4.17 times 4 over 7. All right, 2.38 volts. Which is what we had before. Yay! Okay. So we still need to get IS. So how can we get IS easily? There are lots of different ways to get IS, but IS is the current in this circuit, in that circuit. But we know the voltage of this equivalent resistor, and we know its resistance, so we can let's use Ohm's law for that one. Ohm's law on R2 equivalent says that V1 equals IS times R2 equivalent. So IS must be V1 over R2 equivalent, which is 4.17 divided by 3.733. .12 amps. Yay! Same answer. Okay, what do you know? These things work. Okay, so we did it twice, but let's try it another way. Let's see if we can do this with a current divider. Okay. Okay, so let's get our circuit back here. I guess we'll just kind of draw it like it originally was. Okay. Well, so this one will take a little bit. Let's see what we can do here. 8 ohms, 3 ohms, 4 ohms. Okay, so for the current divider method, we need to know the current flowing somewhere, right, into some resistors in parallel, and then we can say what the currents are from that. So we would need to know, say if we knew IS flowing into this as a combination and this, we could get, what do we call this? I think we call this IA, and we call IA, we call this I1. Right, so current divider would give us a relationship between IA and I1 and IS if we knew IS. And so for this one, we're going to have to go ahead and get IS somehow. So let's say we did this part. So we combined it all down and got our total. So we're going to go ahead and use the parallel series combinations to get IS from our total and the 12 volts. All right, so we get IS is 1.12 amps. Let's do 1.118. Okay, so we can't do it with pure current. It's not as clean as a voltage divider because we aren't given a current, right? We have to get a current to be able to divide it up. All right, so let's say we've done that much work. We've gotten IS. So IS was V source over R total, like we did before. So we got IS. Okay, so now current divider says if we have resistances in parallel, we know the current into the combination, then we can get the current of the pieces. So let's just kind of take a breakdown here, and let's make this one be 7 ohms again, right? Because this is 3 in series with 4. Gives us 7 ohms, right? And this one is the 8 ohms. And there's stuff happening here, but basically we know IS is coming in. We got IA here and I1 here. All right, so as far as the rest of the circuit, it doesn't really matter. IS is a current in this, in all of this, so IS is a current going in there. So IS is coming in. We know the current into this parallel combination, right? So current divider says that, say we want both of them so we can get the voltages. So let's just say we want IA first. So current divider is a little different than the voltage divider. We say it's the total current, and then we put the resistor that is not where we want. So we want the current in the 7 ohm resistor, so we put the other one on top. So think of current divider as being upside down or backwards kind of thing. And then it's again over the total, and so it's over 7 plus 8. Okay, and so again, this in parallel with this is not 7 plus 8, but it's over the sum of the two, is how the equation works. All right, so I guess we can do if we had kind of a general equation, probably I1 is I source times R2 over R1 plus R2, kind of a thing, where you got the current in one, you put the resistance of the other on top. And again, you could have a whole bunch of resistors in parallel and do the same thing. Okay, so we can do 1.118 times 7 over 15, right? So IA is that 1.118 times 7 divided by 15, 0.551. Oops, how did I get a 7 up there when it was an 8? Try that again. 1.118 times 8 divided by 15. That looks a little more like it. 0.59 excuse me, 596, which is what we had for IA before, so that's a good sign. And we can also get I1. So this was just a general formula. I1 for this specific case, again, is going to be our IS, and we want the current here, so we're going to put the other one on top. So now it is the 7 on top, times 7 plus 8. All right, so it's the 1.118 times 7/15, which is the 0.551 amps. Was I1. Which is not what we got before. What did we do? Did we use that for anything? Oh, I typed it in wrong. 1.118 times 7 divided by 15. There we go. 0.522. That's better. 0.522. Okay, so now we can get V1. Ohm's law. I'm going to use ohm a couple of times. I don't know why I always write my H like a M when I start to write Ohm's law. Ohm's law says V1 equals I1 times 8 ohms is 0.5217 actually is what it was, times 8. 4.17 volts. V2 is IA times 4 ohms. So IA 0.596 3 times 4 ohms. 2.38 anyway, 2.39 is what comes out. Maybe I shouldn't have kept that extra sig fig. Just go back. 0.596 times 4. I like it better. 2.38 volts is V2, which is the number we've been getting. Okay. So part of it was like the other one, the brute force method, but then the current divider method then got us that. Seems like maybe a little less paper than the first method, although I didn't write it all out. All right, one more method. Let's get our circuit back again. So let's do the node voltage method. So this is really a more standard actual method, and it's been standardized a lot so that it can be used with computer code and generates the equations in a nice standard form. So we need to learn it. Okay, I think we got pretty much everything there. Okay, so for the node voltage method, we're going to identify our nodes in the system. And so each node will have a name, basically. So let's just, since this is V2, let's just call this node 2. And this has got V1, so let's call it node 1. And let's call this node 3. And then every time we also always have to have a reference node, like a ground node. So let's put a little ground symbol on that and make that be the bottom. It's good to do it this way since we're looking for V1 and V2. It's good to have their minus signs be at the ground node so that when we define what we call node voltages, these are the node voltages. So for the node voltage method, we're going to just say there's a V3 here, there's a V1 here, there's a V2 here. So it's like we're saying the voltage at this point is something. But remember, voltage is always across, right? It's between 2 points. And so what we're saying is V3's positive point is here, but then all of them have negative points at the ground. So V3's positive is here, negative is here. V1 positive here, negative here. V2 positive here, negative there. So the ground reference node is maybe V is node 0 or what have you, but it's the negative for all of the other nodes. All right, so the voltage, even though it looks like we're saying the voltage at this point is V1, it's really the voltage from here down to ground, or to our reference node. Okay, so for the node voltage method, we're just going to do KCL at all of our nodes, or at the ones that make any difference anyway. And so looking at this basic, this is a very simple circuit because there's only one voltage source and so forth, but it's good for them explaining the method. And so looking at our nodes, for this one, for node 3, we have one more node here. Node 4. I missed you, little node there. Okay, so, okay, good. So, that's not 3, that's a 4. So, we know the voltage of this node, but we don't know the current in this source, right? The source is going to hold the voltage whatever it needs to be, and so we don't really know the current there, and we can't, this IS is kind of getting lost in here. We can write the current as IS, but again, that adds another unknown in the circuit. So we will do what we call a super node around that voltage source, but we will figure it out. So let's go node by node and write some KCL equations. So let's do KCL node 1. All right, so we got node 1, and let's do, since we're kind of defining the currents in terms of the voltages, we're going to say that the sum of the currents out of the node equals 0. Right, just because that's the easiest way to write the equation. It makes the equations look nicer. So we've got, for node 1, we've got 3 branches. We want the current going here, current going down, and the current going there, right? Those 3 added together equals 0. So what is the current going this way? We're not going to give it a name, but we know that V equals IR, so I equals V over R, right, for this resistor. Since it's a nice resistor, easy to do the equations. And so the voltage we want the voltage plus here, minus here, because the current's going that way, right? We want current out of the node. So the current going that way means plus voltage here, minus voltage here. It means we want the high side here, the low side here. So the voltage, let's call it Vx for a minute. Vx is going to be V1 minus V2. That's just how it always works. If you do KVL around, you can do negative V1 plus Vx plus V2 equals, let's just go ahead and do that. Do KVL around this loop. We get negative V1 plus Vx plus V2 equals 0, right? And so Vx equals V1 minus V2, right? Same kind of thing we're going to do here if we want the voltage plus here and minus here, right? We call that Vy. We can say negative V1 plus Vy plus V3, V3 comes all the way down here, V3 equals 0. So Vy equals V1 minus V3. Okay, so whenever you want a current going out of a node, you take that node's voltage and you subtract the next door neighbor node voltage from it, and that gives you voltage plus at your node minus the other way, and then you can get the current as voltage over resistance. And so what I'm going to do is say that, so this is not KVL, that's just a side note, but current here, I'm going to say is V1 minus V2 over 3. Right, that's the current going out that way. Right, now I want to add the current going down here. I'm going to add up all the currents going out, so they'll all be plus 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 equals 0. Right, what's the current going down here? Well, the node that we're at is V1, so it's going to be V1 minus the voltage at this node, it's actually ground node, so V1 minus 0, so it's just V1 over the resistance, 8 ohms. All right, now finally the current going this way, V1 minus V3, to get the voltage plus here minus there, V1 minus V3, divided by the resistance of the branch, 2 ohms. right, equals 0. So now we have one equation, 1, 2, 3 unknowns. We need more equations, right? But happily, luckily, whatever you want to say, we have more nodes. KCL node 2. All right, so looking at this node here, node 2, we want to write the equation for the currents all going out of this node. So we want current this way and this way, right? So same kind of process. Current going down here, we've got V2 minus the other is neighboring node, in this case is 0, so V2 minus 0 over 4 ohms. And then we've got the current going that way, so it's going to be V2 minus V1 over the resistance between them, 3 ohms. And there are only 2 there, so equals 0. All right, so now we have another equation between those same 2 variables, and we're getting there. All right, we have 2 more nodes, but we have a problem with this node because we can't write a Ohm's law equation with a voltage source in it. And so what we're going to do is make what we call a supernode. Supernode. All right, so we're going to, the current into and out of any branch or whatever equivalent has to be, KCL has to hold, right? We aren't going to have any current, any charges disappearing anywhere in here. So the sum of the currents going out of this whole blob here have to equal 0 as well. Okay, so we're going to treat that as KCL supernode, I guess we'll call it. All right, so first we want the current going this way. So it's going to be V3 minus V1 over 2 ohms, right? Ohm's law, positive here, negative there, going that way. And then we want the current going this way. So we're going to have V4 minus nothing over 5 ohms equals 0. Well, we got another equation, but we got another unknown. All right, so now we need another equation. Well, so we got the easy equation. Whenever we have a voltage source, that also gives us an easy equation. So for the voltage source, right, we know the voltage here plus and minus here. If we want to do a little KVL around here, however we want to think about it, but we can say, let's just do KVL. Negative V4 to get to here, minus 12 volts to get to here, and then V3, remember, is plus here, negative here, so plus V3 equals 0. So 12 volts is equal to V3 minus V4. So just like we've been doing all this time, if we want the voltage plus here at this node and minus at this node, which is what the 12 volts is, that's going to be V3 minus V4 is 12 volts. So directly we can say V3 minus V4 is 12 volts. Okay, so now we have 4 equations and 4 unknowns. Oh boy. So how do we want to solve these? So this is a general method, right? You can see that you have the process, you go through the process, you can maybe get a mess of algebra. That's why we use matrix theory and have the computer do the calculations for us lots of times when we have large circuits. I mean, you can get like power system circuits or just different kinds of circuits with 1,000 nodes or more than 1,000 nodes, and you have this huge matrix, and we can write these equations as coefficients and then a vector of voltages, and we can have use matrix math to have it find the solution for us. Oh, let's see, what can we do here? We can say that V4 is just V3 minus 12. All right, so then we can put that in here, and so we have V3 minus V1 over 2 plus V3 minus 12 over 5 equals 0. And so now we're back to 3 equations and 3 unknowns. This one relates just V1 and V2, so let's use that to get, let's simplify a little bit. So we're going to have 1/4, let's gather all the coefficients of V2, so 1/4 plus 1/3 V2 minus 1/3 V1 equals 0. All right, so we can have 1 divided by 4 plus 1 divided by 3 is 0.5833. V2 equals 0.333 V1, or V1 equals 0.5833 over 0.3333 V2. 0.58333, a whole bunch of threes, divided by 0.3333. So V1 equals 1.750 V2. Okay. So this one has just V1 and V3, so let's solve. Maybe we should have solved this one for V2. Let's get V2, then just take 1 over that. 1 divided by 1.75. V2 is 0.5714 of V1. Alright, so let's solve this one for V3 in terms of V1. Then we can put it in this equation and only have V1s and get a number. Okay, so here we're going to have 1/2 plus 1/5 times V3 minus 1/2 of V1 equals, let's bring this over to the other side, 12 over 5. It's not as nice. Okay, but we can do it. So 1 divided by 2 plus 1 divided by 5, 0.7 V3 minus, or 0.7 V3 equals 12 divided by 5, 2.4 plus 0.5 V1. And so V3 is 2.5 divided by 0.7, 3.571 plus 0.5 divided by 0.7. 0.7143 V1. Okay, so now we've got this equation, and let's simplify it a little bit here. So all the coefficients of V1, 1/3 plus 1/8 plus 1/2 V1 minus 1/3 V2 minus 1/2 V3 equals 0. All right, so let's get that down here simplified. So 1 divided by 3 plus 1 divided by 8 plus 1 divided by 2 0.9583 V1 minus 0.333 V2 minus 0.5 V1 V3 equals 0. Oh, okay, I think this is getting to be a bit much, but hopefully you can see the light at the end of the tunnel. So we're going to put in V2 into here, this expression for V3 into there. We have an equation in V1. Yes, and there's a constant term there so that we don't just get everything equal to 0. And we can solve for V1, V2 that we're looking for, V3. We'll solve it for V1, and then we can use this to get V2, and then we can use something to get IS. IS, if we want IS, it is also, say, the current here. So IS, in terms of the node voltages, it's the current going this way. So it'd be V3 minus V1 over 2 ohms. And so once we have the voltages, we can get IS from that. Okay, so that's a bit long and drawn out, but hopefully you can complete the algebra from there and see that we would get the same We can get everything we want, and we should get the same answers. Oh, should we just go ahead and do it? I guess I'll just go ahead and do it a minute while I'm here. All right, let's do it. 0.9583 V1 minus 0.3333 times V2, which is 0.5714 V1 minus 0.5 times V3, which is 3.571, 0.7143 V1 equals 0. So V1 equals, bring this to the other side, so it's going to be 0.5 times 3.571 on that side, and then divide through by all the coefficients of V1. So it's going to be 0.9583 minus 0.3333 times 0.5714 minus 0.5 times 0.7143. Okay, 0.5 times 3.571 divided by, in parentheses, 0.9583 minus 0.4 minus 0.5 times 0.7143. Is that right? No. So I get 4.35 volts, but it's supposed to be 4.17 volts. Where did we go wrong? No telling. Okay, so this should have been 2.4, not 2.5. So where is that? So this is 2.4 divided by 0.7, 3.429. 3.429. Okay. 4.17 volts. Whew, what do you know? Okay. So, sorry about that, but that's how it goes. So V2 then is 0.5714 times V1, 4.17 times 0.5714, 2.39, anyway. Pretty close. Rounding errors happening. V3 we aren't asked for, but we need it to get IS, so V3 is 3.4 429 plus 0.7143 V1, 4.17. .41 408. At the moment, I got it. Anyway, sig figs, bad sig figs. Okay, IS then is V3 minus V1. Going off the paper. IS V3 minus V1 over 2 ohms. And so we've got 6.408 minus the 4.17 over 2. 1.12 amps. Okay, so there we have it. It was close for a minute. About gave up, but have several different methods, kind of covering most of the first. So this module is just not all of chapter 2, but a lot of chapter 2. Current dividers, voltage dividers, parallel series combinations, and then finally node voltages. And so hopefully this gives you a good idea. Probably doesn't motivate you to do node voltages very much, but it is the more general method that applies, especially when you have a larger, more complicated circuit that doesn't have just resistances and only one source. If you have multiple sources and odd things going on, it is the method of choice, okay? Because you know you can write the equations, have a complete set, and they are solvable. I guess one thing to note is if you have a current source, what if one of these was a current source? Then the node voltages, the KCL equations become easy for that node because you don't have to do a super node, but you just know the current. So if it was a 5 amp source, you could just put 5 plus or negative 5 or what have you if it's going the wrong direction. So when you're doing your KCL, if you have current sources, they make it easy. You just put in the number that the source tells you. Okay, I think we'll stop there. That one problem done many different ways kind of illustrated most of the things we need for this chapter or this module.